So we're in a position to talk about how you describe scatter plots. We talk about four things: direction, strength, form, outliers. So direction has to do with, as you increase x, does y increase or decrease? So a positive association says if x increase x, then y increases on average. Negative says increase x, y decreases, like that. So for positive associations, you see a pattern where things go up to the right. For negative association, you see a pattern where things go down to the right, like that. So that's direction. It could be curved. It could be a scatter of plots without really much of a pattern. But as long as when x increases, y tends to increase, it's a positive association. If you increase x, x is the horizontal axis in my thinking. You increase the horizontal variable, the y variable, the vertical variable tends to decrease. That's negative. Increasing the horizontal increases the vertical. That's positive. Okay. Then strength, strong, moderate, weak, or no. It says how well can you predict a y from x? So if the pattern is very well defined, maybe it looks like this. And once you pick a horizontal variable, you know what the vertical variable is. You would say strong. Now, sometimes in the pattern of values, you know, it's a clear pattern. You don't know exactly what y is, so we call that moderate. And weak, maybe weak looks like this. Some, but not, oh, maybe something like that. So there's some indication as you increase x, y increases, but you can't tell a whole lot. That's almost no association. No association can happen like this, where when you increase x, y doesn't change at all. Or it could happen because there's a bunch of points, but really, as you increase x, y doesn't change at all. Fine. And then form or shape, linear or curved. Well, it's only on average, so linear, curved obviously might look like this. And linear means falls in a line, like that. But on the other hand, it doesn't have to take on such a strong association type of pattern for you to say linear or curved. Curved could have other values scattered around, so it still looks curved. And linear could have other values scattered along here, but it still looks approximately linear with no clear-cut curve to it. And then we're talking about outliers. Outliers fall outside the overall pattern of the relationship. So ordinarily what will happen is you'll see a cluster of values forming some kind of pattern where you see a cloud of values falling in a certain region. And you can usually identify the cloud like this. That's where you would expect to see values, except maybe there's someone here or here that seems to be disobeying that rule. And those would be the outliers. So outliers may follow the trend line we see here. It might be up here, but it's so far away that you consider it an outlier anyway, even though it seems to be following the same overall pattern. It's not part of this block, so you still call it an outlier. Okay, so that's description. So you can ask yourself, well, here's a scatter plot. Tell me the direction, strength, form, and are there any outliers? Okay, so here are our examples. Okay, so here we're thinking about direction. It looks like positive, positive, That's direction. And then strength, pretty strong here. I would say moderate here. And then shape, oh, linear, pretty much linear. And then outliers. We have outliers here. 2, maybe 3. I think 2 outliers make sense. And 1, it might not really be an outlier, possible outlier. Seemed like it was a little bit offline, but it's not too bad. So whether you call that an outlier or not, it's up to you. These seem obviously to be outliers because they're not part of the pattern. That's sort of not part of the pattern, depending on how your eye sees it. I think my eye saw this, in which case it doesn't seem to be part of the pattern, but your eye might have seen something else. Right. So on we go. It says we're going to find a numerical summary of a scatter plot called the correlation coefficient. It says the strength and direction of linear association can be determined by using the correlation coefficient R. Fine. R, we have some, I think we have more examples of what R can be. Yeah, we do. Okay, fine. So first we're just going to compute it. Here's the formula for R here. Here's our data set here. It only has 5 values. Here's the X and Y coordinates. I copied them from here. So 1, 2, 2, 5, 3, 7, 5, 8, and 6, 11 are the values. And then in order to compute this, I'm going to compute these. These look like normal scores or z-scores. These are sample z-scores for X and for Y. We compute the z-scores, multiply them together, add them up, and divide by n minus 1. N is the number of points. So n is 5 here. So n minus 1 is 4. We ought to be able to do it. I have to find a calculator. Now I think I left my calculator at another location. That might make it harder. I got this one here. It may work. It may not be as easy to read. Oh, it looks like it's all right. Okay. My fancy calculator seems to have gone away. First I need the mean for X. I'm pretty sure we'll add them up and divide by 6. Okay, 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. One, 2, 3, 4, 5. Oh, there's no 4. I was wondering what happened there. 1 plus 2 plus 3 plus 5 plus 6. 5 values. Divide that by 5. 3.4. X bar is 3.4. We're going to need that. And then Y bar is this one. 2 plus 5 plus 7 plus 8 plus 11. Divide that by 5. 6.6. Oh, we need SX and SY. Well, that's annoying. Okay, I'll go stat, edit, come up here, clear that, make that X, come across, go up, clear that, make that Y. Here comes X. 1, no, I don't need a plus sign. I need an enter. 1, 2, 3, 5, 6. 1, 2, 3. It looks all right. Coming back, the Y's 2, 5, 7, 8, 11. Okay. Stat, calc, one variable, list 1. 3.4, we got that. SX, 2.074. Okay, and then we'll go stat, calc, one variable, list 2. And now 6.6, we got that. S for Y is 3.362. SY 3.362. Okay. Now we have to do some calculating. Here's X. Here we go parentheses, X is 1. We subtract off X bar 3.4. And we divide that by SX 2.074. Negative 1.157. Keep doing that. Parentheses 2 minus 3.4. Whoops. Divided by 2.074. Go in here. Negative 0.675. And we do it with 3. Parentheses 3 minus 3.4. Let's see, divided by 2.074. Okay, minus 0.193. Okay, and then parentheses 5 minus 3.4 divided by 2.074. 0.771. 6 minus 3.4 divided by 2.074. 1.254. So those are all the scores corresponding to the x's. Now we do the y's. And we'll be able to check this in a minute. I'm pretty sure I'm probably going to mess this up, but do my best. Here's the y's. Parentheses 2 minus, and y bar is 6.6. Divide that 3.362. 2 minus, I think we're okay. Negative 1.368. And then the next one is 5. 5 minus 6.6 divided by 3.362. So ordinarily when I do this in class, people can stop me when I mess up. Here I'm doing it all by myself. So when I make a mistake, I won't even know. Oh, maybe that's better that way. I'm not convinced. Okay, 7 minus 6.6, close it, divided by 0.32, sorry, 62. So ordinarily, I'll just type the wrong number someplace, and then bad things happen. 0.119. I'm rounding to 3 places, you might have noticed. You can round to 2 probably and still get away with it. Next one is 8. 8 minus 6.6 divided by 3.362. 62. 0.416. Sometimes I'll write the wrong number down and say the right number. Who knows? 11 minus 6.6 divided by 3.362. 1.309. All right, so those are the scores. Then I'm going to multiply them together. Here we go. Minus 1.157 times minus 1.368. Of course, the minus sign I'm using is sitting here. That's subtracting, that's negative numbers. Got to keep that straight. So I got the right numbers. Looks like it's okay. I'm just going to keep 3 places. 1.583. Now you notice when these are both negative, you get a positive answer. So these tend to be negative together and then positive together. So overall, we're going to get a positive answer. That's because with this kind of pattern, if x is below the mean, y tends to be below the mean as well. And when x is above the mean, y tends to be above its mean. So we get negative z's and positive z's, or more or less going together, except for this middle value. Let's do the next one. Minus 0.675. No. Times minus 0.583. 0.301. Oh, sorry, 0.321. Okay, and then minus 0.193 times 0.119. Okay, 0.02, negative 0.023, negative 0.023. A lot of opportunities for error here. 0.771 times 0.416. 0.321. Hey, look, it's there too. 0.32, it's okay though. And here we go, 1.254 times 1.309. 1.641. Okay, keep going with the formula. It says we're going to add these up, and then we're going to divide by 4. First, we'll add them up. 1.583 plus 0.321 plus negative 0.023 plus 0.321 plus 1.641. Double check those numbers again. Okay, go. So we'll get 3.843. And then we said we're going to divide by, the number of points is 5. So then we take that and divide it by 4. Divided by 4. 0.961. So that's the plan for computing. Oh, so I've divide by 4. R to get R, 0.961. And I'll just double check that. There's a way in here. Here's where you go to find R. First thing you have to do is you go to the catalog. It's here, catalog's here above the 0. So I go second catalog. And then I scroll on down to a place that says diagnostics. Diagnostic on. I crank it up and I do it. And now what that'll do is show the correlation when I do the next thing that I want to do. Then I'm going to go to stat. I'm going to calc. I'm going down here to linear regression, which is what we'll be doing after we do scatter plots. Go. And then I have to tell you the list that contain the x and y variables. So second 1, and comma, second 2. So it says, linear regression says we're going to find the least best fitting line to the data. We're not going to do that, but stuff will happen here that will give us the R value compared to what we did. So we crank it in. And there you see right here, R value 96117. Great confirmation that 961 is the correct answer. And the way we got that is by first turning diagnostics on, and then going to linear regression. And there's 2 regressions in there. It doesn't matter which one you choose. And then giving it the X and Y columns where you've entered the data, and out comes the number. So that's exciting. We made that work. Great. And now I'm going to stop recording with that success story.